Welcome everyone to this presentation on logistic regression. Logistic regression is one of the most powerful and widely used classification methods in data science. Despite its name, it has nothing to do with logistics companies. The name comes from the logistic function, which we'll see shortly. Think of it this way: while linear regression helps us predict how much, like predicting house prices, logistic regression helps us predict which one. Which class does this record belong to? In this presentation, we'll cover why it works, how to interpret it, and see it in action with a real fitness center example. By the end, you'll be able to impress your colleagues at the next data science happy hour. Let's dive in. Here's our agenda. Think of it as a journey from "what is this thing" to "I can use this thing." We'll start with the basics. What problem does logistic regression solve? Then we'll peek under the hood at the math. Don't worry, I promise to keep the equations to a minimum and the intuition to a maximum. Then comes the fun part, a real example with fitness center data. We'll see how to predict which customers will upgrade to premium membership. It's like being able to read minds, but with math instead of telepathy. Finally, we'll talk about how to know if your model is any good. Because a bad prediction model is like a broken compass, worse than having no compass at all. Let's get started. Let's start with the fundamental question. What problem does logistic regression solve? On the left, we have our old friend linear regression. It answers how much questions. These are continuous outcomes. The answer can be any number. On the right, we have logistic regression. It answers which class questions. Will this customer churn or stay? Is this email spam or not? Should we approve this loan or deny it? Here's the key insight. Logistic regression actually outputs probabilities, not direct class assignments. It says, this customer has a 73% probability of churning. Then we apply a cutoff, like 50%, to make the final classification. Why is this useful? Because sometimes you don't just want a yes-no answer. You want to know how sure the model is. A customer with 51% churn probability is very different from one with 99% churn probability, even though both would be classified as likely to churn. Okay, here's the challenge. We want to use a linear equation, easy to interpret, but our outcome is a probability that must stay between 0 and 1. The solution: we transform the probability through a series of steps until we get something that can range from negative infinity to positive infinity. Then we can use our linear equation. Step 1. We start with probability P. If there's a 75% chance a customer accepts an offer, P is equal to 0.75, but P is trapped between 0 and 1. Step 2. We convert to odds. Odds is equal to P divided by 1 minus P. If P is equal to 0.75, odds is equal to 0.75 divided by 0.25, which is equal to 3. This means 3 to 1 odds in favor. Now we can go from 0 to infinity, but not negative. Step 3, we take the natural log. This is the Logit. Now we can go from negative infinity to positive infinity. A Logit of 0 means 50-50 odds. The magic: the Logit can be modeled as a linear function of our predictors. Each coefficient tells us how much each predictor affects the log odds. This is probably the most important visual in all of logistic regression, the sigmoid or S-curve. Here's what's happening. On the x-axis, we have the Logit. That's beta 0 plus beta 1, x1 plus beta 2, x2 plus, and so on. On the y-axis, we have the probability of belonging to class 1. Notice the shape. No matter how extreme the Logit gets, positive or negative, the probability stays bounded between 0 and 1. That's the magic of the logistic function. When the Logit equals 0, the probability is exactly 0.5. It's a coin flip. As the Logit goes positive, probability increases toward 1. As it goes negative, probability decreases towards 0. Also notice where the curve is steepest, right around 0.5. This means a small change in the predictor has the biggest impact on probability when you're near the 50-50 zone. Once you're already at 95% probability, it takes a lot more to push you to 96%. This is why we can't just use linear regression for classification. It would give us probabilities outside 0 and 1, which makes no sense. Time for a real example. Let's step into the shoes of a fitness center trying to sell premium memberships. We have data on 5,000 customers. The fitness center ran a campaign offering premium memberships, and only 11.8%, about 591 people, said yes. That's actually pretty typical for marketing campaigns. Our goal: Build a model that predicts which customers are most likely to accept the premium membership offer in future campaigns. This way, the marketing team can target their efforts where they'll have the most impact. We have 12 predictors to work with, ranging from demographic info, age, household size, to behavioral data, monthly spending, weekly workout hours, app usage. We also have categorical variables like fitness level and whether they have a personal trainer. The business question is clear. Given what we know about a customer, what's the probability they'll upgrade? Let's see what the model tells us. Here are our model coefficients, ranked by impact. Green bars push toward premium membership, red bars push away from it. The big winners are Fitness Advanced plus 3.47 and Nutrition Plan plus 1.95. These customers are much more likely to upgrade. Makes sense, they're already heavily invested in fitness. Fitness Intermediate is also positive, plus 1.89, though not as strong as Advanced. There's a clear progression here. Interesting insight. Personal Trainer has a negative coefficient, minus 0.17. Wait, what? Customers who already have a personal trainer are less likely to upgrade to premium? Actually, this makes business sense. They might feel they're already getting personalized attention, so why pay more for premium? Or maybe premium competes with personal training services. Years active is also slightly negative. Long-time members might be set in their ways and not interested in changes. The lesson here: coefficients can reveal surprising business insights. Now let's interpret these coefficients. The raw coefficient, 1.953 for Nutrition Plan, is in log odds, which isn't very intuitive. But if we take e to that power, we get the odds ratio, e to the power of 1.953, which is equal to 7.05. This has a beautiful interpretation. Customers on a nutrition plan have 7.05 times the odds of accepting the premium membership compared to customers not on a nutrition plan, all else being equal. That all else being equal is crucial. We're controlling for age, spending, fitness level, everything else. This is the pure effect of nutrition plan. Why is this useful? Because odds ratios are consistent across the entire probability range. Whether you're going from 10% to 41% probability or from 50% to 88%, the odds still multiply by 7.05. For continuous variables like monthly spending, coefficient is equal to 0.05. The interpretation is, for every $1 increase in monthly spending, the odds of upgrading multiply by e to the power of 0.05, which is equal to 1.05, or increase by about 5%. This is gold for the marketing team. This chart shows what the logistic regression S-curve looks like with real data from our fitness center example. Here, we're using just one predictor, monthly spending, to predict premium membership acceptance. The model found beta 0 is equal to minus 6.23 and beta 1 is 0.04. Look at the beautiful S shape. At low spending levels, $0 or $50, probability is very low. These customers aren't very engaged with the gym. But watch what happens in the middle range. From $75 to $150, the probability shoots up dramatically. This is the sweet spot where small increases in spending predict much higher upgrade probabilities. At high spending levels greater than 175, we're approaching certainty. These customers are extremely likely to upgrade. The practical insight: a customer spending $100 per month has about a 30% chance of accepting. At $150 per month, it jumps to 78%. That $50 difference more than doubles the probability. This is why the full model with all 12 predictors is even more powerful. We can combine spending, fitness level, app usage, and everything else to get much more accurate predictions. Now the crucial step: turning probabilities into actual classifications. The model gives us probabilities, but the business needs a yes or no. Should we target this customer for the premium campaign? We use a cutoff, also called threshold. The standard is 0.5. If probability exceeds 50%, predict positive. Look at the table. Customer number 418 has P is equal to 0.004. That's below 0.5. So we predict no, will not accept. The actual outcome was also no. We got it right. But customer number 1550 is interesting. P is equal to 0.363, below our 0.5 cutoff. So we predict no. But they actually did accept. We missed them. Here's the key insight. The 0.5 cutoff isn't sacred. If missing a potential customer is very costly, we might lower the cutoff to 0.4 or even 0.3. We'd catch more true positives, but also have more false alarms. This is the classic precision recall trade-off. In fraud detection, you'd use a low cutoff because missing fraud is expensive. In spam filtering, you might use a higher cutoff because marking a real email as spam is annoying. The business context determines the optimal cutoff. The confusion matrix is our report card. Let's see how the model performed on 2,000 validation customers. TN, true negatives, is equal to 1,614. Predicted no upgrade, and they didn't. Great. TP, true positives, is equal to 157. Predicted will upgrade, and they did. Perfect. FP, false positives, is equal to 36. Predicted will upgrade, but they didn't. Wasted marketing effort. FN, false negatives, is equal to 93. Predicted won't upgrade, but they actually did. Missed opportunity. Overall accuracy is 93.5%. Sounds great, right? But wait, recall is 62.8%. That means we're only catching about 60% of the customers who would have upgraded. We're missing 40% of potential premium members. Why? Remember, only 12% of customers upgrade. When classes are imbalanced, a model can get high accuracy by just predicting no most of the time. This is why accuracy alone is misleading. For a marketing campaign, recall might matter more. We'd rather have some false alarms than miss half our potential customers. The solution? Lower the cutoff or use techniques like oversampling the minority class. But that's a story for another day. The lift chart is where the rubber meets the road. It answers, how much better is my model than just picking customers randomly? Here's how to read it. We rank all customers by their predicted probability of upgrading, highest to lowest. Then we group them into deciles, 10% chunks. The top 10%, the customers our model thinks are most likely to upgrade, have a lift of 5.1. That means if you target just the top 10%, you'll find 6.4 times as many actual upgraders as if you pick 10% of customers at random. The lift decreases as we move down the ranking. Why does this matter? Marketing budgets are limited. If you can only afford to contact 500 customers, would you rather A. Pick 500 randomly and get approximately 50 upgrades, 10% of 500 multiplied by 11.8% base rate. B. Use the model to pick the top 500 and get approximately 320 upgrades, 6.4 times more. That's the power of a good classification model. Even if overall accuracy seems modest, the ranking ability creates massive business value. Before we wrap up, let's talk about building better models. Variable selection. You don't always need all 12 predictors. Sometimes a simpler model with 5 to 6 variables performs just as well. Methods like forward selection, add variables one at a time, or lasso regularization can help identify the most important features. Best practices. Simpler is often better. Fewer variables means less overfitting. Always validate on data the model hasn't seen. Watch for multicollinearity. Highly correlated predictors can make coefficients unstable. Consider business costs. A false negative might cost $100, a false positive only $5. Test different cutoffs to find the optimal trade-off. Watch out for overfitting. Model works great on training data, fails on new data, class imbalance. When 90% of customers are no, the model might just predict no always. Rare events. Fraud detection needs special techniques. Missing data. Don't just delete records with missing values. The goal isn't a perfect model. It's a useful model that improves decision making. Let's wrap up with the key points to remember. 1. Two-step process. Logistic regression first predicts probabilities, then you apply a cutoff to classify. Don't forget this. 2. Coefficients mean something. E to the power beta is the odds ratio. For the fitness center, being on a nutrition plan multiplies upgrade odds by 7x. 3. Odds are consistent. This is why we report odds ratios, not probability changes. The multiplier is the same whether you're at 10% or 60% baseline probability. 4. Cutoff is a business decision, 0.5 is just the default. In fraud detection, you'd go lower. In spam filtering, you'd go higher. Think about error costs. 5. Lift charts show value. Even a modest model can provide 6x lift in the top decile. That translates directly to marketing ROI. 6. Trust. Validation, not training. A model that's 99% accurate on training data, but 70% on validation is useless. Always hold out data. Thank you for your attention.